Hello, in this video I will be explaining the critical point of a pure substance and just exactly what that means and how we can use the critical point in order to determine certain valuable information for a system that we might be working with. I will also be explaining a pressure versus specific volume diagram and how that relates to the critical point of a substance. And lastly, I will be going through a famous equation of state that was created by a man named van der Waals that allows us to look at a gas in a non-ideal state and use its critical point in order to, again, determine certain valuable information that we can apply to a wide variety of chemical engineering applications. So first here, if we take a look at this basic phase diagram here, this here is a phase diagram for water. However, the information that I will be going through can be applied to any pure substance. So if we take a look here at this diagram, this solid line here separating the vapor and the liquid phase, this solid line represents the equilibrium between these two phases. Now, if we increase both pressure and temperature here, we eventually reach a point here where this dot is. And this dot here is known as the critical point for this substance. Now, in a scientific sense, the critical point of a substance at the critical point and beyond the critical point actually, the properties of both the vapor and liquid phases become indistinguishable from each other. So again, at this point here, this critical point dot, and beyond this point, the properties of both the phases, they'll become indistinguishable. So if we want to take a look at this in a physical sense, if I take this sample of water here in this water bottle, and I want this sample of water to reach its critical point, the first thing that I would need to do is heat this water bottle up so that there's no longer air in this bottle, but that there's water vapor and liquid water, so that it's a pure water substance in the container. But if we got this sample of water to reach its critical point, essentially what it would look like physically is a completely cloudy substance. You would no longer be able to see this meniscus here that separates the liquid phase and the vapor phase in this bottle. So that's the difference between what you would see physically for a critical point sample and scientifically the definition for the critical point. Now, if we take a look here at this pressure versus specific volume diagram, what we have here is we have the pressure plotted on the y-axis and the specific volume plotted on the x-axis, and we have T here, temperature held constant. So if we take here the ideal gas law again, PV equals nRT, and we set the number of moles N equal to 1, we will then be able to set up an expression for pressure that allows us to get these pressure curves. So the pressure expression will be RT over V. So if we have the constant here held, or excuse me, the temperature here held constant and multiply that by the ideal gas coefficient R, we'll have a constant over the x-axis variable V. And we know that plotting any constant over the x-axis variable will give us a graph that goes like this, which we see here up in the top right. So you can reference this to a y equals 1 over x curve. So again, a constant over the x-axis variable. Now, what you see here on the left here is when this substance is at its critical point. Now, again, at this critical point, under this curve here is when the liquid and vapor phases are in equilibrium with each other. And at the critical point here, there's actually two different specific volumes for the vapor phase over here and the liquid phase. So the specific volume of the liquid phase is actually much, much less at the critical point than the specific volume of the vapor phase. And that makes sense. And if we look here under this critical point curve, actually nothing exists here, since there's nothing that exists in reality between the liquid region and the vapor phase. So you just have the liquid region specific volume and the vapor region specific volume. So this all makes sense here for an ideal gas. Now, what if we wanted to take a look at a sample that is a non-ideal gas? How would we be able to plot this pressure versus volume with constant temperature? Well, there was a famous man named van der Waals, and he basically he thought about this a lot apparently because he came up with a very famous equation known as the van der Waals equation of state. And what he did here was he took the ideal gas law, so PV equals nRT, and again holding n equals 2 on to basically ignore that from the equation, and solving for pressure. The first thing that he did here was subtract this B term. And if you remember, in a non-ideal gas situation, the molecules are seeing each other. So the volume of the system that you're working with is not just the volume of the container, but you also have other molecules in that container that are taking up space. So this B here is subtracting that, subtracting those other molecules' volumes, if you will. So this B here is commonly known as the excluded volume. Again, so the volume of the container minus the volume of the other molecules in the container. Now, this second term here, this A over V squared, this takes into account that since, again, it's in a non-ideal gas state, the molecules are forming attractions with each other. And these attractions lower the pressure of the system. And if you want to think of this in a physical sense, essentially the molecules aren't bouncing off the walls as much. So that would lower the pressure. So that is why this term here is subtracted. So using this expression, this allows us to solve for the pressure here. Now, what we can do here, and what I'm going to do in a minute, is we can actually use the critical point here and determine the A and B parameters here for this equation. So what we can do here is we notice that you'll see here up here at the critical point, this graph here, the derivative of it, the first derivative is equal to 0 because you have a flat horizontal line here. Now, what we also notice here is that we also have an inflection point here. So this inflection point tells us that the second derivative of this expression here will be equal to 0. So we now have two expressions. So the first derivative of this van der Waals equation and the second derivative of the van der Waals equation, they're both set equal to 0. So using these two equations, and we have two unknowns, we can then solve for the A and B parameters for the van der Waals equation. So pretty cool stuff here, and what I'm going to do in a minute is actually draw this out, take the derivatives, and show how we can determine the A and B parameters. So that's what we're going to do next. Okay, so now we'll go ahead and derive our parameters A and B for the van der Waals equation. And first, we'll go ahead and start with the van der Waals equation. And just to reiterate here, this B term is known as the excluded volume. Since the molecules in a non-ideal gas state situation see each other, this B term accounts for the various volumes of the other molecules that would be in the container that we'd be working with. And this A over V squared term, that accounts for the interactions between those molecules, which would result in a decrease of pressure. That's why we subtract that A over V squared term. So what I'm going to do here is I'm going to take the first and second derivative of the van der Waals equation and set them both equal to 0. And we know that we can do this because when we looked at the pressure over specific volume diagram, we know that since we can draw a horizontal line at the critical point, that would tell us that the first derivative would be equal to 0. And since there's an inflection point also at the critical point, we know that the second derivative of the van der Waals equation is also equal to 0. So let's go ahead and take those derivatives. So we'll have the partial derivative of pressure with respect to specific volume. Okay, and I'll go ahead and what I'm going to do is basically change these variables to TC and VC for the critical temperature and the critical specific volume to denote that we are at the critical point. That's very important to remember that this is at the critical point. So this here is equal, if we take the first derivative and saying that this V minus B term has an exponent of 1 in the denominator, we will have negative R TC over VC minus B squared. and we'll go ahead and add the 2 in the denominator exponent. We will end up with 2a over VC cubed. And again, this is set equal to 0. So this is our first derivative here, set equal to 0. So let's go ahead and take the second derivative. So if we take the second derivative, again, evaluating at the critical temperature and the critical specific volume, we take the second derivative here, we will have 2R Tc over Vc minus B cubed, and this time we will subtract 6a over Vc to the 4th power and set that equal to 0. So here, these are our first derivative set equal to 0 and the second derivative set equal to 0. And these two equations here will give us our two equations with our two unknown parameters, a and b. So what I'm going to do here is just erase this and rewrite these equations, and we'll go ahead and solve for the a and b parameters. So go ahead and I'll rewrite the equations that we have here. So our first derivative equation, negative RTC over BC minus B squared, plus 2a over BC cubed equals 0. So that is our first derivative set equal to 0, and our second derivative set equal to 0 was 2RTC over VC minus B cubed. And this time we subtracted 6a over VC to the 4th, and that is set equal to 0. So these are our first, second derivatives set equal to 0. Just rewrite that. So what I'm going to do here, we can actually flip this equation here and multiply these equations, and we cancel out a bunch of terms, and it makes it really, really easy. So if we do that, we'll end up with VC minus B over 2 equals VC over 3. And from here, we can go ahead and solve for our B parameter. If we do that, we will see that B equals VC over 3. Okay, so this is our B parameter. Now what we can do here, I can plug this B parameter either into this expression, or excuse me, this equation or this equation. I'm just going to plug it into the top equation in order to solve for the A parameter. So if we go ahead and plug that in, we'll have negative RTC over VC minus VC over 3. This is cubed, okay? And we'll go ahead and we'll actually set this equal to 2a over VC cubed, okay? Now, if we go ahead and simplify this a little bit further, we'll see that we have 9/4 RTC over VC squared equals 2a over VC cubed. Now I know this is a little bit kind of hard to see down here in the middle, so this is 9/4 RTC over VC squared equals 2a over VC cubed. And if we go ahead and solve for a here, we'll get that a equals 9/8 RTC VC. Okay, so these are our parameters for both our A and B terms for the van der Waals equation. Now there is one other thing that I would like to talk about at the end of this video, and that is the compressibility factor for a gas. So the compressibility factor is something that is widely known or widely used in chemical engineering and can be used for a wide application of many things. And the compressibility factor is denoted as Z, and Z is equal to PV over RT. Okay, so that's the compressibility factor. Now the compressibility factor of a gas that's in an ideal state is equal to 1. However, that's not the case with a gas that's in a non-ideal state. So what I'm going to do here is we can actually plug in our A and B parameters into the van der Waals equation and basically derive an expression for the compressibility factor, and it's pretty cool. So let's go ahead and I'll erase this and we can go ahead and plug in these terms and see what we get for compressibility. Move that. So go ahead and rewrite the basic van der Waals equation here. So I have P equals RT over V minus B, the excluded volume, and over A over V squared. So if we go ahead and substitute our A and B parameters in here to the van der Waals equation, we will see that we have P equals, and I'll go ahead and again denote TC and VC to say that this is at the critical point. It's pretty important that we do that. So P equals RTC over V minus, again, V is VC over 3. And we'll subtract here. The A term will have 9 RTC VC over 8 VC squared. And we can go ahead and simplify here and cancel out some terms. So we will see P equals, we'll have 3/2 RTC over VC. And we'll go ahead and simplify here and cancel out. So we'll have 9/8 RTC VC. Okay? So now we notice that we have like terms here in the RTC over VC term. So I'll go ahead and take that out of the expression. So I have P equals RTC over VC. And if we subtract if we subtract 9/8 from 3/2, we'll end up with 3/8. Okay? And if you remember, the compressibility factor, Z equals, that should be a P, Z equals PV over RT. Okay, so that's the compressibility factor. Now what we can do here is we can actually solve for the compressibility factor here in terms of PV over RT. So if we solve for in terms of PV equal RT, we'll see that 3/8 equals PVC over RTC. So what we're saying here is that the compressibility factor for any substance in a non-ideal gas state is 3/8. Now that's pretty cool. We can apply this compressibility factor to any substance in a non-ideal gas state. So that's just something else that we can derive by using the van der Waals equation, and something cool that goes along with the information. So there you have it. Now we have determined the A and B parameters for the van der Waals equation, and also showing that the compressibility factor for any substance in a non-ideal gas state situation is equal to 3/8. Thank you.